attendance today. So I'm Barbara from the SRF User Organization Committee, and today we are very pleased to introduce Marine Cott, the beamline responsible of ID21. So ID21 is a microscopy and now nanoscopy beamline operating in the range of soft and tender X-rays. And today she will talk about what is done on this great beamline and how EBS improved its capabilities.
Thank you very much, Barbara, for the introduction. So indeed, yes, today we are going to talk about ID21, which is specialized in nanospectroscopy in the tender X-ray domain. So maybe as an introduction, I would like to start with two representative examples. These two examples related to cadmium, but in two completely different domains. On the left, it's related to cultural heritage and how in some circumstances, what we call cadmium yellow pigments can degrade. And on the right, it's related to cadmium in the environment. So first, let's start with the cultural heritage context. In this work, the researchers, they wanted to understand why and how, in some cases, cadmium yellow pigments, which are based on cadmium sulfide, they degrade, and which are the parameters responsible for that. So the idea was to see, in particular, on samples taken from the screen, how cadmium yellow degraded. On the right, the context is completely different. Indeed, cadmium is a heavy metal that occurs naturally in soil and which can be absorbed by cacao plants. And the problem is that there are food safety regulations, and in particular in the European Union, which are restricting acceptable concentration of cadmium in cacao products. And unfortunately, for some countries in Latin America and Caribbean, the natural level of cadmium in soil is very high. So there is a concern that farmers may not be allowed to sell their cacaos. So a key question for scientists is, what is the path of cadmium from the soil to the cacao beans? So we have investigated at ID21 these two scientific cases. Here you have a picture of the paint fragments one of the paint fragments taken from the screen painting, which was just prepared as such. And in the case of the cacao trees, different samples were taken in different areas of the cacao trees, in the roots, in the branches, in the leaves as well. And thin sections were prepared using a cryomicrotome in order to see the full structure of the samples. Usually the experiments, they start with X-ray fluorescence mapping, the idea being to get identification of the main elements, so in particular here cadmium, and the distribution of this element over regions of interest. Then we typically continue with X-ray absorption spectroscopy in order to get information about the speciation. And this is very important because it will impact, of course, in the case of the painting, it will define if a sample is degraded or not. And in the case of the plants, it can also say things about toxicity, for example. So for that, we use xanes. So here, for example, you have xanes collected at sulfur KH in different points of this paint fragment. And what we can easily see is that in addition to the reduced sulfide, which is the native yellow pigment, there are also occasionally signals from sulfates, either cadmium sulfate or sodium sulfate. And these two techniques, micro X-ray fluorescence maps and micro X-ray absorption spectra, can somehow be combined into 2D multispectral mapping. So typically what we do is that we select a map, and this map is acquired at several energies. So for example, in this case, we acquired it at an energy which is where sulfides are overexcited, and an energy where sulfates are overexcited. And the comparison of these two maps will tell us the distribution of these different species. And we see that within the matrix of sulfides, there are some agglomerates of sulfates. If you want to know more about these two scientific cases, I invite you to have a look into the respective publications. So indeed, cultural heritage and environmental science are two very strong topics at ID21. And you see the typical questions which are targeted by the users in these fields. Health, medicine, and life science is also a very strong field where many users are interested in understanding interactions which are either incidental or intentional between manufactured materials and living systems. And other experiments can also be related to understanding disruption in metal homeostasis in different diseases. We also have users in the field of Earth and planetary science, typically to get insight into or to obtain chemical signature of different geological processes, and I will give an example later. And occasionally we analyze manufactured materials, in particular phenomena at interferences. So the keywords are identification and location of chemical markers in complex materials. And indeed, if we look at statistics, here you see the scientific domains of the users at the SRF. In red, you have the statistics for the entire facility, and in green, the statistic only for ID21. And you see indeed that we are active in fields which are pretty minor at the scale of the SRF, like earth science, life science, medicine, environment, and cultural heritage, but which are extremely important from a societal point of view. So which are the reasons why users like to come to ID21? Of course, we have expert users, but not all of them. And quite often, we also welcome first-time users. And what they want to obtain is together identification and localization of various species. These species can be major, minor, but also traces. They can be crystallized and amorphous. They usually contain both lossy elements and metals. They are usually in complex and heterogeneous, often biological matrices, and the users, they want to have together imaging with sub-micrometric resolution and sub-millimetric 2D field of view. So what do we offer which fits their needs? We offer a graphical user interface for easy navigation and data collection. We push as much as possible automation and workflows. We offer the two main techniques, X-ray fluorescence and XANES, and we push as much as possible the detection limits down to the ppm level. We also, an added value is that we operate under vacuum, and the energy range is something very specific and very well suited for the scientific cases. We cover from 2 to 10 kV. I will come back to that. Also, with respect to biological samples, but not only, we offer cryopreservation, expertise, instruments, and assistance for sample preparation. Mapping capability, an inline optical microscope. The beam is usually focused, and we have optimized the sample stage and the control to offer fast scanning. Now, what were the directions for the upgrade of ID21? So if we consider the broad domain of the study of metals in biological systems, which represent more than half of the experiments at ID21, there are a lot of technical challenges. It is very important to keep a good balance between three main aspects: the spatial resolution and the possibility to analyze materials from, let's say, the organs level down to the cellular level, to have a very good sensitivity because we want to detect typically metals in the native concentrations, and also the specificity, that is, to be able to determine the chemical state of elements of interest, because this will provide lots of information about toxicity, about evolution of the material. So these are the main directions in which we try to push further the capability of ID21. We targeted a beam down to 100 nanometers, but preserving the field of view and the possibility to study large sample corpus. Also, the beam stability, in particular during XANES scan, is a very important issue. We wanted also to push the flux and the X-ray fluorescence detection. The energy range was already good, but it was very important to go up to the zinc KH because it's an element which is very important in many phenomena. And we wanted to push further the combination of spectroscopy and mapping, a better management of radiation damage, and a better data management. So what has been done over the ID21 refurbishment, which started in 2016? the refurbishment was split into 3 parts. The first 2 parts more about optics, and the third more about the experimental HUTCH itself. And many colleagues were involved in this refurbishment, and I want to thank them. So for those of you who have known or were users at ID21 before EBS, and in particular before 2016, you may remember that at that time we had 4 end stations. We had the X-ray microscope, we had a Xain's full field end station, a diffraction end station, and an infrared end station. And when we started to discuss about the future of the beamline, we decided to be more efficient in one of this activity, and we took the decision to stop the Xain's full field, the diffraction, and the infrared activities in order to concentrate all our efforts and money on the refurbishment of the microspectroscopy aspects. So here you have a timeline of the different things which happened, with a series of shutdowns and interventions at the beamline. In particular, we installed new primary mirrors. We installed the first prototype of the new generation of double crystal monochromator. We got the first EBS beam in January 2020, and unfortunately, COVID arrived, so our activities, the refurbishment and the commissioning was a bit delayed, but still, we managed to have our first users in October 2020, and these users, they could benefit from EBS, remote access, which was super important, BLIS, which is a new control system, and dQuery, which is the name of our graphical user interface. And I would like to use this example of the first EBS experiment because I think it's pretty representative of what we do and what we can offer at ID21. So this experiment was led by Hugo Morera from University of Montpellier. And as you can see on the screen, the title of his experiment was measuring the oxidation state of mantle-derived magmas to assess the role of plate tectonics in atmospheric oxidation. So what does that mean? The story is that around 2.4 billion years ago, there was an event that we call the Great Oxidation Event. And during this period, a significant amount of oxygen accumulated in the atmosphere, which led to a dramatic shift in the composition of the atmosphere. And so the idea in this proposal was to explore how the atmosphere could have also impacted the Earth's mantle by assimilating materials from subducted sediments. So to carry out this experiment, Hugo brought to the beamline a couple of zircons, which were taken from, or which were crystallized in magma formed in an ancient subduction zone. And these zircons, they are containing apatite inclusions that you can see here. And they are dating from this great oxidation event period, just before and after. And before coming, Hugo knew, I mean, it was already known that sulfur is a kind of proxy for the redox conditions of the apatite crystallization. In particular, the oxidation state of sulfur can give you information about the environment, if it was more reductive or more oxidative, and behind that can provide information of the fugacity of the magma. So the very first step was to perform 2D X-ray fluorescence map in order to locate sulfur over the small inclusions, because sulfur is not present everywhere. And for that, we use this dQuery graphical user interface that you can see here, when we can easily navigate and select regions and points of interest. Once we add these maps, we selected a series of points to perform Xain's analysis. So, for example, in this case, over 5 days, we have acquired about 1,600 microxain spectra. And this is a number which is now very common for ID21 to acquire 1,000, 2,000 spectra per experiment. There are reasons for this high number, is that first, we didn't want to stay too long on every point to avoid the risk of radiation damage. And second, it is very important to have a good statistic from one sample to another and within inclusions. And what turned out, the end of the story is that the Xain signal at sulfur was completely different on sample dating before the Great Oxidation event and after the Great Oxidation level, where you can clearly see an oxidation of sulfur that Hugo associated with sediment recycling across the Great Oxidation event. So again, I invite you to have a look to the paper if you want to have the details of this study. So this was in 2020. Then we had another shutdown for infrastructure works. 2022, we were together having users and continuing to design the nanoscope, which was the third part of the refurbishment. So the nanoscope is installed in line with the X-ray microscope. And you have in this slide, oops, I should turn off this one. You have a video of the day when the nano SXM chamber was installed at the beamline. And I would like to take this opportunity to thank so many colleagues who have been involved in this project from all the ESRF divisions. And in particular, the three main ID21 colleagues that you can see on this video. Gaëtan, our technician, Iram, who is the coordinator of this part of the refurbishment, and behind Muriel Salomé, who is engineer at ID21. You may have seen in the last issue of the ESRF News that there was an article presenting feedback from the first users. We welcome our first users February this year. So now we have, I think we had about 10 of experiments using the nano SXM. So what are the main differences between the old microscope that we preserved and the new nanoscope? So both of them, they operate from 2 to 10 kV. Both of them offer micro or nano X-ray fluorescence and X-ray absorption spectroscopies that can be combined into multi-energy maps. They operate under vacuum, and we can work either at cryo conditions or at room temperature. Now, which are the differences between the two microscopes? The old microscope has been preserved to perform analysis with an unfocused beam, so around 100 microns, or with a beam which is focused to about 1 micron, alpha micron, while the objective with the nanoscope is really to reach ultimately a beam of 100 nanometers at high energies. Now we have obtained at best a beam of 150 nanometers above 6 kV. With the old microscope, we had only 1 kb coated with nickel, and so it was making impossible nickel XANES analysis. Now we have 2 kbs, one coated with nickel, the other one with platinum, and it can give, in addition to the access to nickel XANES, we have a much higher flux above 6 kV, which is very important for the detection of metals. And another aspect which will be ultimately very important is the fact that we are waiting for the delivery, complete delivery of 2 5-elements X-ray fluorescence detector, which will give a much better, much more efficient detection than our single element, which is in the X-ray microscope. What does that mean, the energy range from 2 to 10 kV? So here you see in color all the elements that we can detect, so typically from sodium. And the elements which are underlined are those for which we can do XANES, or X-ray absorption spectroscopy. So typically we will cover low-Z elements such as phosphorus, sulfur, and chlorine, and we can do all the 3D transition metals up to zinc. However, we can also analyze heavier metals, for example, cadmium, which I presented in the introduction, that we can study through their L lines. From a practical point of view, something to take into account is a typical sample size that we can accommodate. So with the old microscope, we can mount samples, I would say, as large as 1 inch, 25 millimeters. And in the new nanoscope, the size of the sample is a bit less, but still is relatively good, or reasonably good, about 16 millimeter width and 6 millimeter height. So what it means to practice this refurbishment. So for example, the example I was presenting about cadmium in cacao would have been impossible before EBS because the flux was not high enough. And now we can typically detect metals at the ppm level. Another subject which is more and more studied at ID21 is nanoparticles in the environment. And before EBS, it was extremely challenging to obtain, or above all, before the installation of the new monochromator, it was very challenging to obtain good XANES spectra on nanoparticles because the beam was moving typically around 1 micron. And so we obtain regularly this kind of spectra which are completely useless when we were analyzing nanoparticles. And now, thanks to the new monochromator, which gives a much more stable beam, and the new nanoscope, we have a beam which is staying on the nanoparticle, and we can really collect XANES on nanoparticles. So if I still have a few minutes, I would like to present you with one, maybe 2 examples the performances in recent experiments with the new nanoscope. So the first experiment was carried out by Trinita Pradel. Trinita has been interested in studying lusters on ceramics for 20 years. These lusters, they have these optical effects thanks to the presence of some nanoparticles of metals. And Trinita wanted to get information about copper into this luster. So I recorded a video just to show you how it looks like. This is Mimosa, which is the offline user graphical interface that we can use to check qualitatively the results. So you have here the optical image of the ceramics, and the luster is here on the surface. And typically we start with a large map, which is about 300 microns with a step of 5 microns, which was acquired only in 2 minutes. So just to see where are the main elements of interest. And from this first map, we are going to define a second map where, in this case, the step size was 1 micron, and again, total acquisition 2 minutes, so extremely fast, to get a better idea of the phenomena at the surface. Then a third map was selected, and in this case, step of 0.2 microns, and again, a map acquired in 4 minutes. So it means that we should not hesitate to acquire this kind of maps to get a better idea of the sample. Then we did a couple of XANEs. I'm not going to show you that in detail, but we were also interested in what we call multi-energy maps. So we acquired 119 maps, as shown here, with a step of about 0.6 times 1 microns, dwell time of 30 milliseconds over a region which is both the surface and a bit behind the surface. And so here what you can see are the 119 maps acquired at the copper K edge. And if you click on any of the pixels in this map, you have a pseudo XANEs for every pixel. So it's really the opportunity to have together 2D information and full spectral information. And I have the feeling that this kind of experiments are going to become more and more common at ID21. And so if I wanted briefly to show you another example. If I go out of my conclusion quickly, this is an example which I think is very representative of the capabilities that we have now for the study of biological sample. This case has been gently provided by Manuel González Guerrero, who is interested in iron speciation in nodules from Medicago truncatula roots. So again, they started with a large map, which is about 2 millimeter height, to have an idea of the full nodules that you can see here. Then a second map here acquired with steps of 1 micron, and further zooming in until seeing the individual cells in which points of interest were selected, very easily selected thanks to the graphical user interface, in order to determine the location where the XANEs was acquired. So, take-home message. Why should you consider to come to ID21? Keep in mind that we operate 2D and not 3D, only 2D, X-ray fluorescence mapping, and XANEs which can be combined into hyperspectral mapping. The multi-energy maps, the 120 maps that I showed you, were acquired in only 3 hours, so it's really reasonable. We work under vacuum, which gives a very good detection to low-Z elements. We offer cryopreservation, and the beam size can be either 300 microns or in the range of 1 micron, or down to less than 150 nanometers using the nanoscope. And something which is very specific to ID21, this is the energy range from 2 to 11 keV, or 10.5, meaning from phosphorus to zinc K edge for the K edge XANEs. Finally, I want to take this opportunity to thank first all of you for your patience in connecting to this Zoom meeting. All our users and colleagues, in particular the users who accepted that I show the recent results, all the colleagues involved in the maintenance and the development of our instruments, and of course you are highly welcome to join us for great experiments at ID21.
Thank you very much, Marine, for this very clear and concise presentation of ID21 and novelties. We have some time for the questions. So I guess it's in the Q&A panel that you can ask some of them if you'd like to.
It does not seem that there are some questions so far.
Yeah.
Maybe it was super clear. Also, Iram is connected as well, so don't hesitate to ask questions about.
So yeah, so we have a first one. So it's already a thanks, and because it's very impressive, and to get an idea on how difficult it is to come to ID21. So what is the subscription rate, and how long is a typical experiment?
Thank you, Andre, for the question. So oversubscription, I would say, indeed, it's a bit lower than before, because in the past, since we were offering 4 end stations, we had more requests. Now we are typically have a factor 2. We typically receive about 25 to 30 proposals per semester, and we can allocate around 15. And about the duration of the proposals, I think it happens that we have experiments for 2 days, but it's pretty rare. And it's typically from 3 to 4, occasionally 5 or 6. We were indeed thinking, because we know that our instruments are faster and faster, but on the other hand, also we see that the experiments are getting more and more complex. And for example, these multi-energy maps were not so much feasible in the past, and now we will, I'm pretty sure we are going to do that more and more.
Okay, so there's another question about the analysis, because as you said, there are a lot of data now. So is there a software that enables analyzing the XENS hyperspectral maps to get redox or speciation maps, as you showed in the presentation?
Indeed, there are different solutions. So it depends a bit what you want to do. There are some functionalities already existing under PyMCA. For example, a batch XENS normalization, PCA analysis, NNMF analysis, these kind of things. There is a software which has been used by some of our users, which is TXM Wizard. But a strong, a very important objective for the ID21 team, together with our data analysis colleagues, is to push forwards the implementation of workflows. And more we are using the free Orange data mining software package, which is very nice for designing simple up to complex workflows. And this is really the direction in which we are investing now.
Okay.
Also to automate what can be automated.
Yeah. On this subject, I had also one question, because you were saying there's still a lot of first-time users, and now you are collecting a lot of data. And for instance, XENS is still not maybe so easy to analyze. So are these tools, how does it work for people who don't really know about the techniques?
Yes.
Yeah.
So for us, it's very important that our data is useful. So it's always a pity when you feel that you are collecting very good data, but that the users will not be able to do something from this data. And unfortunately, we don't have time. We cannot commit to process all the data for all the users. So there are different actions that we are doing now. As I was mentioning, we are implementing as many workflows as possible using the ESIF eWorks frame. We are also investing into a better management of metadata. For example, when you select points over a 2D map, there are reasons why you are selecting these points, and you can label your points. Like, for example, high concentration of an element of interest and so on. And these labels are super important for the analysis that you are going to carry out behind. So we have created a loop between data collection and data analysis, such that we can link the label from in the graphical user interface up to the data processing scale. Other actions that we are doing, and this is in particular done by a postdoc, Clément Ollet, we are producing more and more databases of references, such as, and also tools to use these databases, such as it becomes easier and easier to compare a large, very large 1,000 spectra data sets of XEN spectra with references of interest and with, for example, principal component analysis to immediately see groups and how these unknown spectra, how they are similar to some references. So we are really, again, automating as much as possible procedures which are common or which are required by many of our users.
All right. So we have also one question about the EXAFS possibilities on the nanoscope,
Yeah.
especially on zinc nanoparticles, but I guess it can be extended to EXAFS globally.
Yes, alors EXAFS is true that in the past we were not doing EXAFS so often for the reason that I was presenting a few minutes ago, that the beam was drifting. And so it was already at the scale of Xane, so even more at the scale of EXAFS. Now that we have the possibility to keep the beam much more stable, it may be relevant to explore larger energy range to go in the direction of EXAFS. For what concerns zinc, I don't know exactly how far we can go because zinc is really at the maximum of the energy range. So we would have to discuss the exact case, the exact zinc concentration and matrix composition and so on. But it's clear that now that the beam is much more stable, we could think about extending the energy range. There may be a reason why we don't use EXAFS so much is the fact that quite often we are working on complex materials, where in a single spectrum, you usually have a mixture of different components. So it may be challenging to make an EXAFS analysis on the hypothesis that locally the composition is a pure component.
Okay. And now on fields that maybe are not so common at ID21, there's a question about is it feasible to study solid state battery interface and also to perform operando electrochemical measurements?
Operando, we don't offer this capability because we work under vacuum and the environment of the sample is extremely constrained. I did not show you any picture, but basically we have 3 centimeters between the exit of the last mirror and the sample, and these 3 centimeters we need to implement, or we have implemented the visible light microscope and photodiode to measure the incoming intensity beam. So we have so many constraints that we decided not to offer capabilities for what concerns in situ, electrochemistry, gas, or whatever, to keep the high performances of what we do now. We occasionally work on battery interfaces, but I would say without in situ capabilities.
Okay, and also 3D printing or metal additive manufacturing, is it something that can be?
There is nothing that we have done yet on this domain, but I don't see why it would not be possible, again, providing that we are working ex situ. So if a sample is synthesized, and again, I don't know if I mentioned it, but we work on flat samples. So you may need to prepare cross sections or thin sections. Then we can certainly analyze if the question is about, I don't know, metals in polymers or things like this. This is something we can certainly do.
Okay, so now we have a more, let's say, strategic question about infrared. So why is it that it has been removed from the beamline? Because on the 4th generation sources, apparently the results are excellent.
Certainly.
When compared to with AFM.
Thank you, Yves, for the question. So it was indeed a very, very sad decision to take. At a certain point, we had to decide about where to invest in terms of budget and time. And it would have been a pity to have a small refurbishment of the X-ray microscope in order to preserve the infrared microscope. And what we had in mind is that now you have more and more available commercial systems which are based on lasers, which offer resolution like alpha micron, which was pretty good. I mean, which is exactly what we would have liked to offer to our users. So we decided, because it was very complex for the colleagues from the machine to maintain an extracted infrared beam with the EBS design, And because we needed to concentrate on the refurbishment of the X-ray microscope, we decided to stop the infrared activity, having in mind that when we have the budget, which is not yet the case, but maybe if some of you would like to share with us €500,000, we would be very interested in investing in a laser-based infrared microscope, commercial infrared microscope.
Okay. So yeah, now one more question about the Xanes, about the drift. Is there something to maybe how much is it, and is there any procedure to correct this effect?
Yeah, indeed, this question is very important, very interesting. There are two aspects. The drift due to energy scanning, we have calibrated that, and when we do regular Xanes, we are below 50 nanometers, so less than half of the size of the beam, clearly. However, this does not mean that the drift during multi-energy map is also 50 nanometers, because many things can happen. The sample can move, the beam can occasionally move, for example, because there is whatever thermal evolution, a refill or something like that. So we know that over 3 hours, if not more, it may happen that let's say the maps are going to shift one respect to another. And indeed, within our workflows, we have a step which corrects that. So if you are interested in copper and you consider that you also have calcium with a very spotty distribution in your sample, you are going to use this extra element in order to realign your maps and to have at the end a perfectly aligned set of multi-energy maps.
Okay. And maybe the final question is about analysis with PyMCA. If there is an online tutorial or online resources to help the users?
Yeah, not yet, but that's a good suggestion. I'm sure within the team there will be colleagues or myself willing to produce another video, because this is something we try to do more and more, to record ourselves and to post how-to videos on YouTube or on the SRF web pages. So Yingming, to answer your question, yeah, exactly. You can. I would advise you to use ROY imaging, but there are certainly things that we can do better than the simple tools offers in ROY imaging. So more to come in a few months.
Okay. So I think we're okay with the question. I have to add that everybody was thanking and saying bravo for the presentation in the open questions. So well, I thank you again. And maybe I just have the announcement for the next seminar of this series, which takes place on January the 16th next year, and it will be on ID10 about the surface scattering end station.
Thank you, Barbara.
Thank you, everybody.
Bye.
Bye-bye.